Okay, let's go ahead and move on to heaps and heap sort. We've talked about balanced binary trees, which are one type of binary tree. Heaps are going to be another type of binary tree that are actually, well, let's put it this way. Heaps are one of these data structures you should keep in your back pocket because when they fit like a perfect glove and they're perfect and beautiful, everything's great. But most of the time they are not a good solution. But when they are, it's great, it's amazing. So we're going to talk about what a heap is, which is a type of binary tree that maintains the heap property. We'll go into that. And then you can actually use it to do a heap sort, which is an in-log-in algorithm in order to sort anything, really. All right, so why study heaps? Well-known traditional sorting algorithm. Heap sort is always in-log-in. Quick sort's usually in-log-in, but heap sort can guarantee it. Quick sort, although ends up being usually faster, but heap sort's better in critical time situations. Okay. Ooh, this is very important to understand as a programmer. What this means is on average, quick sort is faster, but heap sort is more predictable. So, if you have a critical time application, I don't know, you're trying to fly a plane and you need to respond within a certain time, and your two algorithms is quick sort, which has an incredibly wide I guess range of how long it takes versus heap sort, which is pretty constant. You want to use heap sort because then you can predict how much hardware you need, how much money you need to spend on hardware in order to maintain your algorithm. While quick sort, you're going to have to always go with the worst case. So, oh yeah, does that make sense? That is very important to keep in mind. What is a heap? All right, definitions of heap. Hey, have we talked about a heap before?
Yep.
Yeah, what was it?
It was memory.
It was memory, yeah. So a large area of memory for which a programmer can allocate blocks as needed and deallocate them when no longer needed. The data structure, a balanced left justified binary tree in which no node of a greater value than the value is a parent binary heap. What's the relation between these two? Nothing.
A node is a pointer.
Literally nothing.
A node is a pointer.
That's right.
That's about it.
What's that?
Trick question?
Trick question. Nothing. Unfortunately, look, I didn't do this, but now a heap can mean one of two different things inside of this course. Sorry, guys. That's just how it is. I didn't call it this.
They seem to do that a lot.
No. A stack, because there is the memory stack and there's the data structure stack. The memory stack operates just like the memory structure, the data structure stack. They are basically the same thing. Just one we're explicitly talking about in a class, the other one's implicit to how recursion operates. So with the stack, it is the same thing. It's the exact same thing. Heap, it's completely different.
Why did you give their name?
I agree with you 100%.
Because someone wasn't looking at their textbook whenever they made the data structure, or vice versa.
That's it.
Yeah.
That's the only possible explanation.
They made this
Alright,
great thing and then
let's call it.
forgot that the thing that they're naming it after looks nothing like the thing they just made.
Yes. And then the name stuck, and yeah. Well, I mean, have any of y'all taken EE?
What?
Electrical engineering?
I said PE.
Oh no.
I was like, I haven't taken PE in like 7 years.
Hey, this look fit to you.
Wait, they don't make you take PE in high school?
No, they do. But freshman
No.
year, I took it in 8th grade.
No, I took.
Wait, hold on. Let me
Yeah.
rephrase this. They didn't make you take PE every year of high school?
No.
We had
Wow.
one PE
Well, that was
credit we had
different.
to pass. I'm
I
glad.
had the choice of either NJ or TC or
Yeah, we had the same choice, but I was like,
I didn't have a
uniform or run around in circles.
band.
No, I had to still do both.
Oh,
Band and
I guess
PE.
my high school was slightly better because you had to take PE, and you could either run around in circles or use it as study hall.
Oh no, we
Study
didn't
hall.
get study hall. We had
I wish
test
they
and
had
PE.
that.
We had to learn all the different stuff about each
Is this
sport.
public school?
No, I did that too.
Public, yeah.
Well, you went to private, right? Huh.
My public
What's
school,
up
you
with
had to learn
schools?
everything about each sport and then take a test on it.
Yeah.
My
Wow.
PE
They gave us the answers
was,
before though.
my PE was like 1/2 actual like PE and another half sex ed.
Oh, that's how mine
Oh,
was
then,
too.
I think that's the way they're required to do it, so.
But it was more like
Oh no, I said
Nothing
not.
like
Now,
that.
when y'all were in elementary school, did you have to take child abuse training?
No.
What?
Good.
What does that mean?
Excuse me?
I don't know why they call it this, but no, they teach elementary students how to watch out for pedophiles and whatnot. I call it child abuse training.
I thought that would be something completely different.
Oh no, that's what
Teach
they
kids
did.
how to fight.
Oh, you mean recess?
What do you mean recess?
Wow. All right, back to the heap. All right. These two definitions have a little in common. I basically say, okay, sure. They both deal with memory. Heaps use the second definition, so sorry about that. Balanced binary tree. All right, recall the depth of a node is the distance from the root node. Oh wait, why did I erase this? Ooh, I can still see it.
Because it never really erases from the wall.
And
9 is the other one.
we're going to stop here. So that's a balance and left justified. If I put a node right here, it is not left justified because the next node needs to go right here. So I'm going to put it over here. This is not a binary search tree. That's why these nodes are out of order. So there's just a binary tree, but it's left justified. The next node needs to go right here. Next one's sure right here. And then of course right here. So it's balanced. Basically it fills it going from left to right.
What's the point of a binary tree if it's not sorted?
Hang on. That is an excellent question. And we will get to it because a heap is a binary tree, but it's not quite sorted the way you want it to be sorted. It's going to be a little tricky. Because the binary search tree was intuitive because you just go left and right. This one's going to be different. All right, depth of tree, we're going to go through a bunch of definitions. A binary tree is balanced if at all nodes of depth 0 through n-2 have 2 children. So this is balanced. This is balanced, but it's not left justified. In other words, full, 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 but only the last row is not full. It's balanced. I mean, it's missing one there and missing one there and 2 here. It's still balanced. It's just not left justified. Not balanced because there's a node missing here, so you should need to take one of these and move it up there, or take that guy and move it over there. All right? How are we doing?
5.
Great. Left justified. Left justified. Wow. All the leaves same depth, and leaves at the n+1 are on the left of the node. So left justified, no staying over here. Not left justified because there's this guy over here needs to be shifted over here, and this guy over there, and then it'd be left justified. So you fill it from left to right. Okay, great. Plan of attack. First we'll learn how to turn a binary tree into a heap, and then we'll learn how to turn a binary tree back into a heap after it's changed in a certain way. Great. Finally, this cool part, we'll see how we can use this idea to sort in an array. Beautiful. Heap property. All right. So a heap is a balanced left justified binary tree where every node maintains a heap property. So this is going to be the difference, because in a binary search tree, it didn't care about the balance or left justified. It just had the whatever property, the binary search tree property, where everything to the left was lower than, everything to the right was greater than. Heaps are going to have a different property, so you have to remove that property and have a different one. If the value in its node is large or larger than the value in its children.
Large or larger? What does that mean?
As large, sorry.
Oh, the same or bigger.
I forgot the word. So, has the heap. Blue node has the heap. Blue node does not have the heap because the 14 is larger. So let's go over here. Woo. Let's see if we can fix this. So let's look at these three. The 5, the -2, and the 7. Is that a heap right now?
No.
No. We need to, let's fix that by moving the 7 up. 7 up. All right. Let's look at the 20 next. It's in the right spot? No. Where's it need to go?
-2.
I'm going to help you out. So we'll put it up to -2. Now let's look at these three. Are they in the right spot? Nope. What do we need to do?
The 20 needs to go up.
Yeah, the 20 and the 7 need to go up. All right.
Now it doesn't matter if those bottom 2 are in order, does it?
We haven't gone to these 3 yet. So we're just looking at these 4. Oh yeah, they don't have to be in order. Who cares?
Okay.
19. Is he in the right spot?
No.
No. I just called 19 male. So,
Assume my gender.
oh, I will assume. Okay, is 19 in the correct spot now?
Yes.
All right, let's add that 8. Is it in a good spot? 8's
No.
male again.
Wait, wouldn't 10 go up? Oh, you go
We haven't got to the 10
9.
yet.
Yeah, I get the end.
Now we'll do the 10,
Oh my goodness.
and then the 10
Goes up.
goes up. All right, now is it a heap?
Yeah.
Every node is greater than its children. Yep. All right. What is one property you can say about the root node of the heap?
It's the biggest.
It is the largest. That is the most important thing to keep in mind of a heap. The top node is the largest. Can you say anything else about the rest of them?
They're all
Besides-
less than.
They're all less than it, correct? And each node maintains the heap property. That's all you can say.
So how would you like assign nodes to that?
Oh, yeah, we will get to that.
You just throw it on there.
So
And then you go through the.
I wanted to give you the high-level view of what's going on. We're going to talk about adding and removing in a moment.
Cool, because I'm mystified.
All right. All leaf nodes automatically have the heap property. You know, since you don't have any children, you're obviously as large or larger than them. Of course, you're also small or smaller, but that's okay because there's nothing to be larger than. Perfect. A binary tree is a heap if all nodes in it have the heap property. All right, again, just to make sure this is clear, there are different types of binary trees. We've talked about binary search tree. Today we're talking about the heap binary tree. Sifting up. So if we want to add something, we need to be able to sift up. Given a node that does not have the heap property, you can give it the heap property by exchanging its value with the value of the larger child. So, blue node does not have the heap property, so what do?
Move the 14 up.
Move the 14 up. Oh, look at that animation. This is sometimes called sifting up. Notice the children may have lost the heap property. Really? Okay, a tree consisting of a single, so how do we construct a heap? A tree consisting of a single node is automatically a heap, right? Because it's one node. It's a great data structure. You have one node, it's everything. It's a linked list, it's a binary tree, it's an array, it's graph, it's everything we want. So we construct a heap by adding one node at a time. Perfect. Add the node just to the right of the rightmost node in the deepest level. If the deepest level is full, start a new node. Examples. You're here, add new node there. If you're here, you got to add node there. All right, how are we doing? That means if we want to add a node to the one up there, give me a large number. We'll say 40. Perfect, thanks guys. It needs to go over here. So that's step one. Part 2, each time we add a node, we may destroy the heap property. Right, -2 no longer has a heap property, so we need to sift up. But each time we sift up, the value of the topmost node in the sift may increase, and this may destroy the heap property of its parent node. We repeat until we're done. So, for example, does -2 maintain the heap property?
No.
No, so we need to sift up. Great. Does 19 still have the heap property?
No.
No, so we need to sift up.
Oh, this is the first nightmare.
Okay. Now, does the 20 have the heap property?
No.
We're going to sift up. And then we're done because we're up to the top. Very important observation, incredibly important. Do we need to go and reevaluate our child here? No, because since the number increased, making it larger, it still implicitly has the heap property. So we only have to sift straight up in a line, since all the numbers are only going to increase. What does that mean that insert is in the big O? O of?
In login.
We're not doing it in times.
Login.
Log in. Is that best, average, or worse? all three. Because it's balanced, left justified. So that means that the binary tree will always be full. So that means inserting into a heap is always log of n, period. There's no times where it gets unbalanced. Hey look, it's the first type of balanced binary tree. But it's not a binary search tree, so you can't use it for your project. Okay. Let's go look at the slides a little more. So we keep doing it, and we reach nodes whose value don't need to be swapped because the parent is still larger than both children, or we reach the root. Great, so let's talk about this. We got an 8, we added 10, what needs to happen?
Sift up.
Yep, sift up. Beautiful. So we added a 5, do we need to do anything? Nope. We added a 12. Oh!
Just sift straight up.
Well, you gotta sit not straight, you gotta do it one at a time.
Yeah.
Yeah, so first with the 8, and then again with the 12. Boom. Other children are not affected. Move with the 14. The node containing 8 is not affected because its parent gets larger, not smaller. That's why you only have to sift straight up. You don't have to search or scan the entire heap, because since you're already guaranteed you're maintaining the heap property and the values are getting bigger, there's no need to keep searching. Is that clear? I hope so. This went from a 10 to a 14, so you don't need to search the 8 because the number went larger and you already knew that that value was smaller. Great. And of course we finish up there. Node 5 is not affected because parent gets larger, not smaller. Beautiful. The node containing 8 is still not affected because although the parent got smaller, its parent is still greater than its original. Yep. All right, a sample heap. After it's been heapified, that is an official term.
But I can make another word.
Heapified? What would you prefer besides heapified?
I meant besides heap.
Heap? Oh well.
Shuffle.
Shuffle? Do the shuffle?
I like that word.
Notice that the heapified does not mean sorted. Is this sorted?
Oh no.
Oh my, no. Heapifying does not change the shape of the binary tree. This binary tree is balanced and left justified because it started out that way, and a heap always maintains a balanced, left justified binary tree. Man, I don't know how many times I'm going to say that today. Balanced, left justified. Hey, removing the root. Starts with an arrow, apparently. We have to, all right, so if you're going to remove the root, the first thing you do, what, you pour a root?
Yeah.
Pour a root. All right, let's go do it on the board first, and then we'll watch the slides. So if you're removing the root, and why would we remove the root? Because the root has one thing we know, and that is?
It's the biggest.
It's the biggest. Spoiler alert, if you keep removing the top, you can sort something. Whoa! So what we do is, since we want to maintain the balanced left justifiedness, if we're going to remove that one, then we need to remove the last node, which is going to be the last one on the binary tree. So that'd be the -2. We put it up here. All right. Does it have the heap property? Nope. What do we do?
Just swap it with 20.
With 20. Why did we swap with 20 and not 10?
Because it's bigger. It's also the left, and you start on the left. Right?
No.
What you were doing?
It's bigger. It's because the 20 is bigger. Because if you swap it with the bigger of the two, then you know that the heap you don't have to do the rest of this, right? Because you've chosen something bigger. So we'll swap it. Does this have the heap property?
No.
So which one do we swap it with?
Right.
19. Are we done?
Sure.
Let's try
You
that
gotta
again.
check the 7.
Yes. Why do we have to? No, we don't.
Yeah.
No?
No, because when you were here, you chose the bigger of the two, right? So since you chose the bigger of the two, you knew this number has to be bigger than the 7.
Okay. I'm just getting confused because earlier you always checked both sides.
Oh, for the heap property of which one? No, when you were down here and you went up, you
No,
checked.
whenever you had the full tree and you were completely sorting it, I guess. or
Oh,
not
oh,
sorting
you're
it.
confusing with the binary search tree. Yes. The binary search tree, you have to check both sides. In the heap, you check both sides to which one's bigger. So it's just when the check is made. So
Okay.
binary search tree, you check it as you're going through. This one, when you're percolating or sifting down, you check which one's bigger and then you swap with the bigger one. And the reason for that is since you know it's bigger, you don't have to go and check the other side.
So is it easier just to take the last node and put it in the root? Or
You have to take, the reason you have to take the last node and put it in the root is so that you guarantee that the heap remains balanced and left justified. So by swapping it, you maintain your balance and left justifiedness. You're done with that. Now you just need to arrange it so it stays a heap. That's why you always choose the last node. And now we're back to a heap. What was the big O of this?
log in?
Why is that?
Because that's what this one always has.
That's what this one always has. Notice every time you percolate down, you're chopping off half of the tree, right? So it's log of n. Bless you. Hey, that's great. Insert and remove is always log of n. That's handy. All right, so in this one, we had the example. We're going to remove whatever the root was and then move the 11. Why are we moving the 11 up there?
That's the last one.
Because it's the last one, and what does that maintain about our heap?
Balanced.
And
Left something.
justified. Left whatever. The two words you keep saying, Dr. West. How can we fix the binary tree so it's once again balanced and left justified? We remove the rightmost. Oh yeah, we already wrote. You already gave us the arrow. Sorry. There we go. Boom. Oh, it's beautiful. Ooh, look at that.
Fancy.
Now we have to reheap it because the 11 doesn't have the reheap. It's like heating, only heaping instead. So what do we need to do first?
Pick the biggest of its children.
Which is the,
22.
and move it to the,
11.
all right. How about that? Swap it. Since we chose the largest of the two, we no longer have to look on the right side, which cuts the searching in half, which is why this is log of n. All right, does the 11 have the heap property?
No.
No, so what are we going to swap it with?
22.
22 again. Again, since you chose the largest of the two, you cut off this half of the binary tree. Now we're at the 11. Do we have the heap property?
No. Nope.
Nope, so we're going to swap it with the
21.
21. So we sift it up. And why are we done?
Because there's no more children.
There's no more children. He's childless. Yep, that is why. All right. How we doing? Largest store value is in its root. We can repeat this process until the tree becomes empty. And why would we want to repeat this process until the tree becomes empty? Because then we'd get all the nodes starting from the
Largest to the smallest.
smallest, which would make it,
Sorted.
whoa, okay. From largest to smallest, aka sorted. All right, so sorting. All right, here's the big trick. And this is usually the part where students have the hardest time, so let me pause